All right, so cubics, this example will be a little bit quicker than the rational one, the rational one from examples earlier and the square root one, but only if you really recognize that binomial expansion pattern, which is being demonstrated down here. And remember, if I put anything inside of here with this x or y, it hits the same thing that is going on with the powers. So for example, if this had actually been like 3x plus y squared, then this would be 1 times 9x squared, because I'd have to take that first term and square it. Then this is just a coefficient, but there'd also be a 3x in here, so this would become 2 times 3x, so really it would become 6x. And then back here, it would just be 1 because there would be no first term back there at all. So if there's a coefficient in there, it hits the same pattern. This 1, 3, 3, 1 are just the coefficients from the binomial expansion. If there's any additional coefficient in here with these terms, they're going to get these powers hit to them as well, and then multiplied by what's out in front. So that was just kind of a quick refresher on binomial expansion. So of course, for my needs, what I've done is I'm just going to find the derivative of x cubed, because I don't really want a whole bunch of crazy stuff going on. And the reason this is up here is that if I'm going to use the limit definition of the derivative, then I'm going to find the limit as h approaches 0 of f of x plus h, which in this case is x plus h cubed, minus f of x, which in this case is just x cubed, all over h. And now I can expand this using the really this one, because I don't have any extra coefficients in there. So this is going to continue to equal the limit as h approaches 0. And if I expand this, I'm going to get x cubed, and I'm going to get 3 plus 3x squared h. This is again the binomial expansion coefficient, and it shows up again, but now my x goes from a power of 3 a power of 2 down to a power of 1. H is increasing in power. It's now h squared, and then 1 is my coefficient in my last term, and I cube this thing, so h cubed. So that's the expansion of this, and I still have this minus x cubed on the back all over h. So this is why I said this one's going to be a little bit quicker. Notice that this x cubed, boom, cancels with this minus x cubed, and now every term has an h in it. So if I want to continue this, I just say the limit as h approaches 0, because I've yet to plug 0 in for h. I can factor an h out of this, which would leave me 3x squared, and an h out of here, which would leave me 3xh, and an h out of here, which would leave me h squared. It's a good thing I changed colors. That's all over this h in the bottom, and once again, that's my goal, because I don't want the h down in the bottom. I want it to cancel, and it cancels here. So it's gone, and now I can take the limit. I can put this this 0 in for h right here and right here. And so if I do that and take the limit, then I get a derivative of 3x squared. And this becomes 3 times x times 0, so that's gone. Plus 0 squared, that's gone, and that's my answer. Derivative of x cubed. The derivative is 3x squared. So your job is to pause this thing and determine the derivative of this. This 2 is not part of the x cubed, so it would, when you do your difference quotient, it's going to be 2 times x plus h cubed minus 5, and then minus 2x cubed. So it's a little tricky. So you got to expand this, and then once you've expanded it, distribute the 2 to each of those terms that I have up above. All right, give it a go. Pause, actually, sorry, pause video. Okay, should have done it. Shouldn't have taken you as long as the square root one. And here's how fast I can do it with just understanding a pattern. That derivative is 6x squared. That's what you should have gotten. Okay, short video. Probably first time ever video under 5 minutes.